Hello everyone. Today we will discuss about Young's double slit experiment. Before going into the details of double slit experiment, we will recall the interference of waves and the condition for interference. Interference, it is the phenomenon of one wave interfering with another and the resulting redistribution of energy in the space around the two sources of disturbance. When waves interfere, they can interfere in two different ways. They can interfere constructively and destructively. As shown in the picture, there are two waves, 1 and 2, with amplitudes E1 and E2. They interfere here in such a way that their crests interfere with each other. Their crests coincide each other, their troughs coincide each other. Such a kind of interference is known as constructive interference. They are said to be in phase with each other, the waves. At the point where they interfere in phase. Therefore, we get constructive interference. And there is another case in which the crest of wave 1 coincides with the trough of wave 2. An example of destructive interference. There are various ways of interfering other than this crest and crest trough. But we will go with these two cases and conclude that in order to have constructive interference, the waves must fall in phase with each other, and for destructive interference, they must fall out of phase with each other, as in the second case. And when they coincide out of phase with each other, if both of them have the same amplitude, then the interference is said to be completely destructive. The resultant amplitude is 0. We say light also possesses the properties of waves. The question here is, if light also behaves like waves, is there a chance that there is complete destructive interference take place and light add up to give darkness? The answer to this question is yes. Since they are waves, light waves can interfere destructively also. We have enough examples of constructive interference of light. Two light sources give the intensities of two light sources add up to give more intensity at the region where they happen to coincide. But is there any chance that they interfere in such a way that darkness is created where they fall? If light is wave, light possesses wave property, then that should also happen. Thomas Young, using his double slit experiment, proved this. He proved the fact that light and light add up to create darkness. The very famous experimental setup looks like this. For the experimental setup, there are two slits S1. In the experimental setup, there are two slits S1 and S2 created close to each other, which are illuminated by another source behind it, as shown here. That is why it's called the double slit experiment. Two small slits. And light from these two slits fall on a screen kept at a distance d, as shown here. What happens here is, these two slits now act as sources of wavefronts according to Huygens principle. They can emit wavefronts, they can act as sources of wavefronts, they can behave as individual sources. And when light starting from the source 1 fall on the screen, light wave from the other source also can fall on the screen and interfere at a point on the screen. The place where they interfere how they interfere, constructively or destructively, depends on the condition for interference. There is one more condition for interference in the form of path difference also. We can state the condition for interference of waves. If there is a difference in path between the two waves from the source 1 and source 2, and if the path difference is equal to integral multiples of lambda, equal to n lambda, where n is equal to 0, 1, 2, 3, etc. mathematically, where lambda is the wavelength. At all positions where the waves, when they interfere, satisfy this condition, those positions will have constructive interference. And at all positions on the screen at which the path difference of the two waves is n plus half lambda mathematically, where n is equal to 0, 1, 2, 3, etc., they interfere destructively. Coming to the pattern on the screen, the pattern looks like this. These are two different patterns for two different setups. The pattern can look like this. On the screen, what you see is this, which means that there are regions where you observe complete darkness and there are regions where you observe brightness, which means these are the points, the dark, these are known as the bands, interference bands or fringes. You get dark and bright fringes on the screen, which is kept at a distance from the two slits. Depending upon the slit separation, the shape of the fringe can slightly vary, but still you get dark and bright fringes. Now, these fringes are formed according to the conditions for constructive and destructive interference. We will derive the conditions that a point on the screen may be a bright or dark fringe point, fringe region. This is the experimental setup, the diagrammatic representation of the setup, for which you have the source 1 kept here, source 2 kept here, separated from each other by a very small distance d. Practically the small distance could be less than 1/10 of a millimeter for clear, distinct fringes. And on the screen at the midpoint, what you get is a bright fringe, because the midpoint has path difference from source 1 and source 2. Path difference between the waves from source 1 and source 2 at the midpoint is 0. When there is no path difference, according to the condition, it must represent a bright fringe. The question here is, a point P here on the screen, an arbitrary point on the screen, will it be bright or dark? The answer to that question is, it depends on the condition of interference. If the waves from source 1 and source 2 interfere constructively there, then that point corresponds to a bright fringe. If they interfere destructively there, then that point corresponds to a dark fringe. So, we need to calculate the path difference here. The difference in path travelled by the waves originated from source S1 and source S2. The difference in path is to be calculated. So we will make use of this picture for calculating the difference in path. What we need to calculate is S2P, the straight line displacement, minus S1P. That is the difference in path. If you calculate, to calculate that difference in path, let's consider a triangle. Here, for that triangle, S2P square is equal to D square plus D by 2 plus X the whole square. It's a simple calculation. Similarly, S1P square can be calculated to be D square plus X minus D by 2 the whole square. So considering S2P minus S1P as the path difference, we make use of this diagrammatic representation in order to calculate S2P minus S1P in our way. S2P square is equal to D square plus D by 2, which is half the slit separation, plus X the whole square. S1P square is equal to D square plus X minus D by 2, half the slit separation, the whole square. That's it. and we will rearrange it. So just the rearrangement says that S2P square minus S1P square is equal to, substituting the corresponding values, you get 2xt. Now splitting this S2P square minus S1P square, you get S2P minus S1P into S2P plus S1P is equal to 2xt. It can be easily verified, this 2xt. And looking at this construction, since this distance S2P, S1P and D are comparable, compared to this distance of the point where you want to find whether it is constructive or destructive interference, this distance is small, very small. For that condition, you can assume S2P to be approximately equal to S1P to be approximately equal to D, and therefore this term is 2D. So the path difference S2P minus S1P is equal to 2xD divided by 2D, which gives you path difference to be equal to xD by D. So we derived the expression for path difference in Young's double slit experimental setup. This is not sufficient. We need to know what this path difference represents for this particular point under consideration. Now we will see if that path difference is equal to n times lambda as mentioned earlier, then for n is equal to 0, 1, 2, 3, etc., you get bright fringes on either side of the screen. Of course, as mentioned, x is equal to 0 corresponds to the central bright fringe. Now, putting n is equal to 1 for this expression, you have the first bright fringe from the center. On either side of it, you get. Similarly, for path difference is equal to 2n plus 1 lambda by 2, another condition, another way of representing it, where n is equal to 0, 1, 2, 3, etc. On either side, you get bright fringes. For example, putting n is equal to 0, you get the first dark fringe to be at d lambda by 2d, and proceeding like this, you can find the fringes, the positions where you get dark fringes. Now, coming to the fringe width, the position difference between two consecutive bright or dark fringes will give you the width of the fringe. For both dark and bright, the width of the fringe can be calculated by, say, xn, the nth bright fringe minus xn minus 1, the n minus first bright fringe, which gives d lambda by d. This term is known, this is the expression for width of the fringe. So finally we got a situation where for a setup like this, on the screen you got dark and bright fringes, which is an interesting result of Young's double slit experiment, because it proved that bright and bright, two light waves can create darkness. They can add up to produce darkness. With this experimental setup, Thomas Young proved that light can behave like waves. Light has all the properties of waves. Light waves can interfere constructively as well as destructively. Coming to the intensity variation. This is the pattern of intensity variation, the variation in intensity of light at various points on the screen from the center on either side of it. You can see at the center the intensity is of some value, and just at the dark fringe position you have intensity minimum or 0. The intensity remains almost the same for all the bright fringes in this case, and intensity remains almost the same, close to 0 for all dark fringes here. And in order to have the sustained interference on the screen, the waves need to satisfy certain conditions. The conditions are as follows. The two sources producing interference must be coherent. The two interfering waves must have the same plane of polarization, and the two sources must be close to each other. As I mentioned earlier, these two sources must be as close as possible to get distinct fringes of the order of 1/10 of a millimeter or so. And the sources must be monochromatic. If not, the fringes will be colored and will overlap. And the waves must have the same amplitude for complete dark regions. So with this study, it was proved that light and light can superpose to give darkness. Some examples of daily life examples of interferences: the light from a film of oil floating on water and light from a soap bubble. These are some of the examples. So that's all for today. Thank you.